Welcome back to Physics 11. Today we're going to be looking at Hooke's law. Now, Hooke's law deals with the spring force or the elastic force. So the most common example you can think of is your regular coil spring. But as you can see here, we have a person jumping, looks like bungee jumping from a bridge or a crane. So another example, welcome back to Physics 11. In this video, we're going to be looking at Hooke's law. So Hooke's law deals with the spring force or the elastic force. So again, the most common example of this would be a coiled spring or an elastic band. So let's take a look at some examples. So again, the force, when we talk about the elastic force, we're talking about the force that works to return a distorted object to its equilibrium or to its original position at rest. So let's say if you take an elastic band, you stretch it, and you let it go, it will come back to its original position. So some examples of objects that you can think of that this force might act on, of course, would be spring, elastics, let's say bouncy balls. But this also applies to things that perhaps are not made of springs or rubber. For example, a hockey stick, when you shoot the puck, actually also bends and will deflect basically a certain distance. So in reality, any object that you bend or compress will have an elastic force. So hockey stick, let's say a bow or a crossbow. Of course, shocks on a car, which could be leaf spring, for example. Even a plastic ruler, right? You can bend it and it will come back to its original shape, hopefully. So there's lots of different examples you can think of in this case here. So let's take a look at the actual definition in terms of math. So it's defined by the following equation: the elastic force equals to K times delta X. So in this case, the K is a constant and delta X is the distance which the object was compressed or stretched. And again, the law itself is the size of an elastic force is proportional to the distortion of the object. So again, the distortion here is represented by the constant of the spring. So each spring has its own constant and how much it was actually stretched or compressed. So in this case, delta X is the distance, could be positive or negative. So positive or negative. And I also wanted to mention that in the textbook, instead of delta X, they use delta L to represent distance or change in length rather than change in distance with the X. But again, it means the same thing. So again, K itself is a spring constant, and depending on the material that the spring is made from or on the size of the spring, the coefficient is going to be different. So the stiffer the spring, the higher the spring constant value is going to be. And the units are newtons per meter. And the constant is going to be, again, dependent on the type of material that it's made from. And delta X is the distortion from equilibrium or from rest, and this is measured in meters. So whether you compress it or you stretch something, whatever that change in length is going to be our distortion delta X. So again, the textbook uses delta L instead of delta X. It has to be meters, so if you have something like centimeters or millimeters, make sure you convert it to meters. And again, read the questions carefully because sometimes your delta X has to be negative, sometimes has to be positive. So here's an example. It says a student stretches an elastic band with a spring constant of 50.0 newtons per meter by 15 centimeters. How much force are they applying? So here's what we know. Oops. Let's come back. We know that the force, or sorry, the constant is 50.0 newtons per meter, and delta x is 15 centimeters. So the first thing to do here is to convert our units for the delta x to meters, because we need meters, not centimeters, keeping the same number of suffix. So the unknown is RFE. That's what we need to find here. So all we have to do, we don't really need a free body diagram for this. We just need the equation for Fe, because that's the only force we care about. Take our, delta, let's write the K first and then delta X. Plug in the values for our K, which is 50, which is 3 suffix here, 0.15. All right, so 50 times 0.15, we get 7.5. And the units should be newtons here when we're talking about forces. So again, if you keep the units with your calculations, that can help you identify any mistakes. So for example, if you do dimensional analysis on this equation, we have Fe equal K times delta X, and you look at the units, we have newtons for the force, we have newtons per meter for the K value, and we have meters for delta X. As you can see here, once you multiply K and delta X, the meters cancel out, we left with newtons on both sides. That's what we expect to get for force. All right, so let's take a look at the second example. So in this case, Al McInnes uses a wooden stick with a spring constant of 850 newtons per meter. So as you can see here, this is not a spring or an elastic, right? But again, because you can bend the stick, we can still use the same principle, the same equation, to see how much force, or whatever, in this case, we're looking for the distance that it was actually bent or deflected, and we can use the same Hooke's law to find this. So in this case, what we know here is that the spring constant of the stick, K, is 850. All right, we know that he applies a force, spring force of 525 newtons, and what we don't know is our delta X. So that's the unknown. So that's why I use Fe rather than Fs, because it's not always a spring, but when you say elastic force, this can apply to any object. So let's write our equation. Delta X times K, well, I guess it doesn't matter. We have to solve this for delta X in this case. So we're going to solve this for, again, delta X. So we had to divide by K both sides. So force divided by K. And then we can plug in our numbers. So let's write delta X on this side. Plug in force is 525 over 850. So we have 3 suffix on the top, 2 on the bottom. So 525 divided by 850, we get 0.6. Let's see, 2 suffix, we had to round to 0.62. All right, so this is 62 centimeters. So maybe units that are easier to understand. That's how much the stick bends when he loads up for a shot. All right, let's take a look at the last example. So here we have a 65 kilogram girl sits in a redneck slingshot that had a spring constant of 10.5 newtons per meter. If the sling is stretched by 45 meters, what is her initial acceleration when released? Now, be careful here, because when you draw the free body diagram, because we have multiple forces acting here, before release, let's do 2 diagrams. So before release, we have, let's say this is the girl, we have force of gravity, let's say she's sitting in a chair or on the ground, whatever, and there's going to be normal force, and let's say this is going to be the force of the elastic acting this way, and then we have someone's holding her from the back, or maybe it's friction, she's just using her legs. Let's call it friction. Right, so we have all these forces acting on her. But this is before release. Once she's released, there's no longer normal force, there's no longer friction. The only force in the x direction is going to be the elastic force, and we don't really care about the y direction in this case. But after release, or pretty much at the moment of release, the only forces that will act on her is going to be the elastic force and force of gravity, right? So she's in free fall basically, and at the moment of release, we only care about these two forces, or actually really just this one. That's the only force that's going to be actually making her go, let's say, in this case, to the right. So in the x direction, our F-net equation is just going to be the Fe. So if we made this positive, it's going to be positive, and this is going to equal to our m times ax. So again, the only force we care about here is Fe. Fg, the y direction altogether we don't really care about. So this is the only force, so we can replace our Fe with the k times delta x equal to ma, right? Because we're looking for the acceleration, let's solve this for a first. So divide both sides by m, so we get k delta x over m equal to ax. So let's write this on this side. Plug in the numbers for k, delta x, and m. So k in this case, spring constant is 10.5. Delta x is 45 meters, and the mass was 65. So we have 2 sig figs, and 3, so the answer should be 2 because we're multiplying and dividing here. So 10.5 times 45 divided by 65, we get 7 let's see, we get 269 meters per second squared, but we're going to round this to 2, so 7.3 meters per second squared. Okay? So that's the acceleration after the release, or basically at the moment of release. Once she's actually in free fall, the only force acting on her would be force of gravity, nothing else, if we ignore air resistance. But anyway, that's the acceleration. So I originally did not have any worksheets for this section, but I found some and I attached them to the video. So make sure you do the questions attached to this video. So the two PDF files, one of them is the blank and the other one is the solution. So in the textbook, you can also read about force of friction, but the textbook kind of goes a bit more into details, which is not really physics 11 material. So for example, if you go into the textbook, you can see that it talks about Hooke's law, and as you can see here, they use delta L instead of delta X. But after this, they go into more details and they go into the elastic modulus, which is really not something we're going to be looking at in physics 11, but you can do the questions if you wish. The math is not hard. It's just basic algebra here, but yeah, they go into more details, which again, you don't really see in physics 11. You would see this in perhaps first year physics course, or if you go into engineering. So do the practice questions that I attached. If you have any questions, let me know, because like I said, I found the worksheet. I didn't make it up myself. So if there's any mistakes or anything like that, let me know.